Hey, John here. There's something weird about this program. Let's make sure that we know exactly what's happening. All right? So I went out and grabbed the standard, and I used my usual using statements up here so I can use the short names. I wrote a function here called dump. Let's look and see what the arguments are. I have an unsigned 8-bit. That's actually down here, an unsigned 8-bit. This is a signed 8-bit, a signed 16, an unsigned 16, signed 32, unsigned 32, and a Boolean argument. Okay? And when I go down here, I want to print it out. I'm going to have a little heading at the beginning of the line that says, oh, yeah, I got a signed 8-bit value. And it's going to be a hex number. And so I'm going to print a leading 0x, set the hex mode, and I want 2 digits. I've got a 0 over here to make sure it prepends, it puts a leading 0 in front of it, and I want to print it out because I want to see it. If I print a 0F or something, I want to be able to see what the value is. And then again, I want to see the decimal value as well in parentheses over here. I do the same thing for the signed and unsigned 8s, 16s, 32s, and I want to do the same thing for Boolean. I want to see what the value of a Boolean is if I print it out in hex, all right, as well as in decimal, all right. So that's what this little dump routine does. And I'm going to call it in this program example down here. I create a bunch of variables of the appropriate types. Just for fun, let's go ahead and print out the size of each of these things, right? Size of is a compile time operation that takes place. This whole thing will be replaced with the literal value. This is the same thing as, in this case, you're going to see it's going to do what you think. It's going to replace this entire text will be replaced with the number 1 from the perspective of the compiler, right? So the compiler will see a double left in the number 1 in here, and this will see a double left in the number 2. This doesn't get run at runtime, is my point. This is not a subroutine that will get executed later. It'll get done during compilation, okay? So we'll be able to see how big each of these things are. This is just for fun. Let's print out how big is a Boolean. All right, the size of function is defined as returning the number of bytes of memory that's consumed by the variable that you name in here or the data type that you name in here. I've obviously used data types rather than the variables. So how big is a Boolean? You might think it's 1 bit, but a computer can't load and store 1 bit. It has to at least load and store a byte. It could be any size, really. So let's find out what it is on this machine. It also could vary between different operating systems and stuff like that. So just for fun, let's see how big a Boolean is. We come down here and we do what? We're going to set all these things to 0. I'm going to set the Boolean to a false. I'm going to call the dump routine. This is fun. Let's see what happens to this Boolean variable when I set it to false. I'll do the same thing. I'm going to set all my integer variables to a 1, and I'll set the Boolean to a true and dump it again. So we'll be able to see what what all this stuff is doing. What happens if I set everything to an 81 down here? Is this even legal? What does it mean to set a Boolean variable to the value 81? All right. Well, we'll find out in a minute when we dump it out. And then, of course, the program ends like that. Okay, so let's go ahead and compile it. Let's run it and see what we got. So the program starts running here. Here's my size ofs. I print out the sizes of everything, and nothing surprising here. An 8-bit value is 1 byte, and the 16s are 2s, and the 32s are 4s, and a Boolean is 1 byte in size. All right, so there's 8 bits of memory used on this particular machine to store a single Boolean. What should, logically, it's only 1 bit. All right, so that turns out to be, that's how much memory will be consumed. I set them all to 0 and I print them all out. Remember, I set the Boolean to false, and then I printed it out as a hex value and a decimal value, and I ended up getting a 0, and that kind of makes sense. Here's the other guys going backwards. We run into these 8s, and this is why we're looking at this. What's up with that? You saw the code. I printed these out the same exact way as I did these other ones, and yet there's something broken here. We'll come back to that in a minute. Set everything to a 1. Well, everything looks good here. The true, remember I said the B equals true, and it gets printed out in decimal and in hex as a 1. There's still something broken with these guys. Now, what happens if I set everything to an 81? Well, these guys down here look good. I remember I set my Boolean variable to 81, and then I called the routine to print it out in hex and decimal, and it's a 1. So, first of all, why did the compiler not even complain, right? Shouldn't you set those to 1s and 0s or trues and false or something? Well, I set it to 81. So let's figure out what's up with that and what is up with these Qs in here. Huh? Okay, so that's weird. So let's jump around a little bit. Let's look at the manual page for the ASCII character set. What is the decimal number 81 in the ASCII character set? Surprise! It's a capital Q. So that should give you some insight what's going on here. All right? It didn't print the 81. Even when I set the mode to hex, you'll notice, it printed out the letter Q here. Now, what's up with the 0Q? And what's up with the blanks up here? Well, it turns out that when you print an 8-bit value to see out using the insertion operator, it formats it as a printable character. And if you print out a 16-bit signed binary value, it formats it as an integer. Okay? Same with a 32-bit. The Boolean, how does it format that? Well, that too is an integer. Well, why is this a 1, not an 81? Okay, it's weird. And where did this 0 come from over here? What's up with that? Let's take care of this 0 first. And this blank stuff first, okay? Let's go back and look at the ASCII man page again. Remember, I set the values to 0, and I set them to 1. Then I set them to 81 when I called the print routines. Well, it turns out there are no printable character glyphs for these two codes in 0 and 1. So there was nothing for it to print. These are control things like start of header, the null, start of text, end of text. These are like for modem handshaking and communications and stuff like that. I could have put a 10 in there if I wanted to as a character, and it would have put a new line on the screen or a vertical tab or the tab character. I could even make the screen ding, right? You know, when you're editing and you hear a bell from your PC, that's decimal number 7. If you put a 7 in there, let's just do that for fun to see if I'm joshing you, right? Instead of putting 81 down here, let's put a 7 in there. Or at least in one of them, okay? Now listen closely. Did you hear the ding? Let me turn up my speakers in my basement here. All right, so when I run my program, it goes ding. Now notice what get printed out on the screen here. All right, I got nothing followed by the Q. Let's look at the source again. What am I doing? I said I want a 2-character wide value when I print the contents of my signed 8-bit integer here. Okay? My S8 comes from here. I need 2 characters on the screen, and I want to see it in hex. Now all this prints after I say S8 equals 0x. The very next character after this comes from the insertion operator trying to print S8. Look at the rules. I want 2 characters. I want the value in hex. And I want all leading characters to be 0s. So what did it do? When it printed the bell, what it did is it printed a single character. Therefore, in order for there to be 2 characters on the screen, it put the leading 0 in there because I said set fill to 0. It then sent the 1 character code to the screen. which doesn't show up visibly here because there's a space. If we go back at the source code again, there's a space. I print a space and an open parenthesis myself. There's nothing here. That's because the bell sounded. It doesn't show up on the screen. It makes a tone. When it was the 81, it knows it's only going to print a single character, so it has to pad the left with a 0. This is really confusing if you're not thinking about it right, okay? Then I print a space and an open parenthesis, and then I say, I want the decimal value, please. And it doesn't give me the decimal value. It gives me the character code. And then there's a close parenthesis and an end of line. So, oops, that's running it again. Okay, so let's look more closely at this. So what's going on, right? All right, so there's the 0x again, and I want 2 characters. It knows it's only going to print 1 character, so it puts a leading 0 in front of it. That's what explains the 0x0 followed by nothing for the bell, and the 0x followed by 0q for this one here, because remember when I wrote it out, I set the signed value to 7 and the unsigned value to 81, which is the code for a capital Q. So that explains these 2 lines here up to this point right here. The space afterwards, after the Q in this case, and the open paren come from here, and then I say, please do this in decimal, and yet it does not. I said I want decimal, and yet it doesn't. It prints it as a character, okay? So why does that happen? That's the whole point of this dialogue here. What's up with that? Well, let's see what happens. Let's recompile it once more to see what the command is that it used to compile this program. Let's look and see what's really going on if we say expand the include files and then stop running the compiler. Show me what we're doing here, okay? First of all, let's go to the bottom of this file and hit Control-G. I hit capital G to go to the end of the file. We can see that there's 37,000 lines and change in this file. The very end of the file is where my code goes because there's no includes down there. If you look up near the top of my program up here, the include files are all expanded. So once the include files up here are done being 37,000 lines of expansion there, it then gets to my code down here. That's why you can see my code as I typed it in. So again, we've got the decimal values. You can see what's going on in here, all right? So what's up? What the heck is going on? Why is that not printed in an integer form? I mean, the other ones are. It stands to reason. It should be fine. Let's see what this really is. Remember, I had to include, this is a C++ program, and I included C standard int.h. Let's go ahead and look at the source one more time at the top. Remember, I did this. I want the standard integer representation. I want the names so I can use these. You know, I go through all this hassle and yet it doesn't work. Okay, let's look and see what happens when we expand the include files. Now, I'm not going to go through all 37,000 lines. That's foolishness. Let's come back up here and say, look, an unsigned 8_t. Where did that come from in the include files? Let's just search for it. Unless you can type / and you can give it a text string which says go find this in the file, and you'll see it highlights it. Okay? Now let's not confuse ourselves. If I search for an int 8t, look what happens there. If I search for an int 8t, it highlights the match. Look very closely. Because I searched for an int 8, it also finds the int 8 right here that is part of the text uint8. Okay, now make sure you keep this in mind because there's all kinds of other things that might have an int8 in them. So I'm going to hit 1G to go to the top of this file, and then I'm going to hit N to say search for the next occurrence of what I'm looking for. First thing I find is this thing called typedef. I say typedef signed character, and you see a double underscore int8_t. Well, that's not int8t, that's something else. And that's why we need to make sure we keep our eyes on what we're searching for here. This is not what I'm looking for. I want to find the thing that's just int8t. You can see a double underscore uint8t in there as well. You see something else happening. Again, that's not the thing we're looking. This is not the variable you're looking for. Aha! There's the one that we are looking for. I got a typedef. I have this weird double underscore thing, and then I have the one that I'm looking for right there. Okay? What does this mean? That's what I want. Int 8 underscore t. Typedef. What's that thing doing? What this is doing is it says, I want an alias. In my code, treat any variable whose type is int 8 underscore t as if it were instead this thing over here, a double underscore int 8 underscore t. Okay? So this simply says, I want an alias. I want this data type here, the type definition. I want to define a new type. That's what that stands for, in terms of another type. So in the source code, I type int 8 underscore t, and the compiler goes, okay, that's really a double underscore int 8t. So now we care about the double underscore int 8t. We want to look for that thing, okay? Here we are. I'm searching around. It's jumping around on me. I'm sorry. Okay, so here's where we are. Typedef, this new thing, as an alias for the thing that's highlighted right there. So I'm searching for this double underscore int 8t thing, and it says, oh, I can't find any. Well, I'm going to hit 1G to go back to the top of the file, because maybe it's before that, right? And then hit N to go to next. Well, this is the thing we were looking at earlier. Now, actually, it is important to us. So what does this one do? Right? It says, well, double underscore int 8t is the same thing. It's an alias for assigned character. And now we see what's going on. When I said I want to int 8 underscore t, the compiler said, oh, well, that's a double underscore int 8 underscore t, and that is really assigned character. So if you look at the source code, what's going on in here? What does it mean to the compiler, right? Here's where the function dump is. I really have effectively said, I want an unsigned character called, or rather, I'm sorry, this is a signed character called S8. This one here would be typedef to double underscore uint 8t, and then that would be typedef again to unsigned char. Okay, so these two are actually characters. That's why when I printed it, it printed it as if it were a character, even though I asked it to do otherwise. All right, the insertion operator is overloaded. Okay, it says, oh, I recognize this as a character, so I'm going to print it as a character. If it was a pointer to an array of characters, it would print it as a string. If it was an integer type, it would print it as a number, and so on. Okay, so how then can we get what I want, right? Let's remake this program here and rerun it. Oops. There's my bell again. Let's fix this so it's not belling all the time. All right, so we want to put this back to an 81. And let's look closely at what's happening up in here. So the problem is somebody's trying to do us a favor that we don't want right now. I mean, normally, more often than not, if you give this cout object, if you use the insertion operator, I should say, on the cout object, and you give it a character of some kind, it makes sense that it would print it as such, right? So how do we get this thing to not do this? Well, there's a couple of ways to solve this problem. One way is to just use a brute forced cast. Now, we have to be careful that we don't break our variables, right? If it's a signed 8-bit value and we want to see it expressed in the form of an integer, what we can actually do is convert it to an integer first. Now, we could use like a basically old school C-style brute force cast to do this. This is one way to do it. I have a signed 8-bit value, but I know that the compiler is treating it like a character, or more accurately, the insertion operator for the cout object is treating it like a character, and it does special things that I don't want it to. But I know if instead it was an int 16t, which is something that will not cause it to be broken. If I change it, right, what am I doing here? I'm doing a sign extension from a signed 8-bit value to a signed 16-bit value. It will not change the value of that variable if I sign extend it, okay? If I chose the wrong data type here, I could wreck the thing, right? If I chose an unsigned 16t, it might cause other things to happen. That would effectively make it 0 extended, right? Well, it turns out, since I'm only printing 2 characters anyway, you could do this incorrectly and get away with it. Okay, let's do the signed one and leave the unsigned one alone for reference, and just recompile and run this now and see what happens. Oh, look what's happening. Now we got a hex 51, which is a decimal 81. And all these, so it's doing the same thing these guys do. It prints the right number of characters, it prints the correct decimal value, all is well. And that's from the beginning, right? If I wanted it to be 0, I see it as a 0. Now I see it as a 1, and that all works. And now I got my 81. Everything looks pretty good right now. Okay, let's look at the other one now that we know how to fix this. Now, if you're a diehard C++ person, you might say what you really want to do is a static cast. Well, in this case, you would want to use uint16 in order to use 0 extension on these unsigned values, right? So let's go ahead and do it again for the decimal value. So this is a C++ type cast. And it should do the same thing. So you could do it either way. The C-style casts are sledgehammer solutions that the compiler won't warn you about if you do it wrong. The static cast allows the C++ compiler, these are only available in C++, it allows the C++ compiler to help you if you don't do this right, okay? So you really should use the right kind. If you're in C++, you want to use the static cast. And now you can see, and whether you do it the old school brute force way like I did for the signed value, or the unsigned with the C++ style static cast, all is well and everything is fine, okay? So what's the lesson here? Be wary of typedefs, okay? Especially if you're going to use the value of a variable with a typedef data type. Think about what that means, right? When you pass it to something that's been overloaded. Okay, so this all prints out fine. Where does that leave us with our binary? What's up with that? Well, the rule for binary is, or a Boolean, I should say, binary variables, a Boolean is that C++ provides the word false is another name for the number 0. And it provides the word true as another name for the value 1. In fact, I don't know this, but I suspect I could do this here as well, all right? For reasons we'll talk about in a minute. Down here, when I'm assigning an 81 to this variable, and what's going on there? Okay, well, just like this up here, which we'll see, I'm sure will compile okay, for a similar reason why this compiles okay. It turns out the compiler helps you. It will coerce a value of one type into a value of a different type if it needs to do so in an assignment or a mathematical operation. So what I've done over here is I put an 81 in there in decimal. That is what we call a literal. It literally, it is something that means the literal representation of what you're looking at on the screen. Okay, it's an 81 in decimal. It's an integer. Compiler sees, oh, he typed 81. I'll create an integer, and in binary, that'll be a 32-bit integer. It's even signed. And it says, okay, fine. I got that value now stored in an integer. Then it comes over here and it says, all right, I need to assign that value to this Boolean thing over here. Well, what does that mean? Well, a bool is something that can only have a 1 or a 0 stored into it. It is a different type. And what it does is it says, well, I can convert an integer to a Boolean. And the algorithm it uses is precisely this. If the integer happens to be 0, then it will assume the value is false. If the integer value is not 0, it'll assume that the value is true. Therefore, that's why 81 is true. Okay? And true is a 1. That's how it got to be 1. Now, what's going to go on up here? I bet that this will be a 1. And I'll bet it even compiles okay. Not a problem. And I even have warned against all possibly conceived weirdisms. Okay? So what's going on there? Well, the same thing can happen. When the compiler gets over here, it sees the word true, and it says, oh, okay, that's a Boolean value, and it's not false, therefore I'll make it a 1. It's not a 0, therefore it must be a 1. And it allocates its 8 bits, and it stores that 1 in those 8 bits. Then it sees the assignment operator over here, says I need to assign that to a variable that holds an unsigned integer. Well, I can convert that by just doing a 0 extension on this thing. And it does. So when we run this, you'll see the case up here, which is right here, where I assign a 32-bit value that's an unsigned integer, the value of true. So what's happening in this program? What's the point of this entire discussion? Well, you need to keep aware when something's trying to help you by converting data types from one type to another, and you need to know what the rules are. Anytime you store a value into a bool, it will be converted to an 8-bit value that is either a 0 or a 1. And anytime you take a bool, even if it's a literal, and assign it to something that is an integer, it will 0 extend that Boolean value appropriately and take the resulting value and store it in the integer variable. All right? So make sure that you think about things from the perspective of the compiler, because remember, what you're doing is you're writing code that represents instructions to the compiler. You're not writing code as instructions to yourself. You know what you want. You have to express exactly, precisely what you want to have happen in a way that the compiler will do what you want it to do. All right? So this is a trip up. I actually fall prey to this all the time. I'm constantly going, oh, I forgot. Once again, I happen to have an 8-bit value or something like that, and I start seeing characters when I really wanted to see, integer numbers and stuff like that. And I got to go back and add my casts as appropriate. All right? So don't get thrown. Don't get stuck on this. All right? I always keep a wide open mind of what things mean from the perspective of the compiler. So thanks for watching. See you next time.